Welcome to The Explainer. Today, we're going to unpack how a computer actually learns to think. It's a fascinating story that starts with something as simple as a single line and ends with the deep, complex blueprint behind modern AI, the neural network.
So how does a machine actually learn to tell the difference? Well, the secret isn't some giant complicated rule book for what a cat or a dog is. Nope. It's about teaching the machine to see patterns and, most importantly, to draw a line.
All right, Section 1, Teaching Machines to See. The core challenge we're really giving an AI is a task called classification. And at its heart, it's a surprisingly simple idea. It's all about drawing lines.
Okay, so picture this. You've got a chart with blue dots and red dots just scattered all over the place. The goal of classification? It's simple, really. Draw some kind of boundary that cleanly separates the blues from the reds. We just feed the machine tons of examples. You know, this is a cat, that is a dog. And its whole job is to figure out for itself where that dividing line needs to go.
The very first crack at this was back in the 1950s with an invention called the perceptron. Now think of it like a really simple gatekeeper. It just looks at the evidence and makes one single decision, yes or no. For our dots on the graph, this means it could do one and only one thing: draw a single, straight line.
Section 2, the simple neuron's limit. I mean, for really simple problems, this thing was amazing. But what happens when one line just isn't enough? As researchers pretty quickly discovered, that single line limit, well, it turned out to be a massive problem.
Let's take a look at a super simple logic problem, the AND gate. The rule is easy. The output is only true if input 1 and input 2 are both true, right? So if you plot these four possibilities on a graph, you end up with one lonely true dot that we need to separate from the other three false dots.
And for our single little neuron, this is a piece of cake. It can draw one straight line and cleanly slice that true point away from the other three. Boom! Problem solved. Super easy.
But then research just slammed into a wall. And that wall was a logic puzzle called XOR, which stands for exclusive OR. Now with XOR, the output is true only if the two inputs are different. So if you plot that on a graph, things get tricky. You get two true dots in opposite corners and the false dots sitting in the other two.
And this little puzzle, it perfectly shows the fundamental limit of a single neuron. I mean, go ahead, try it yourself. Try to draw just one single straight line to separate the true from the false points. You can't do it. And this XOR problem, it actually stalled progress in AI for years. The perceptron was completely stuck.
Section 3, Power in Hidden Layers. So how did they finally break through that wall? Well, the solution was just beautifully elegant. If one neuron isn't enough, what if we just use a whole team of them?
And that breakthrough was the multi-layer perceptron, or MLP for short. What researchers did was add a brand new layer of neurons right in the middle. They called it a hidden layer. Think of it like a committee of gatekeepers. Each little neuron in this hidden layer is its own decision maker, just like our original perceptron.
Okay, and this is where the magic really happens. Each one of those neurons in the hidden layer, it draws its own straight line. Then the final output layer looks at all those lines and combines their decisions. It can learn a rule like, hey, the answer is true only if we're above line 1 and we're also below line 2. See? By combining these simple lines, the network can suddenly carve out these complex, nonlinear shapes and solve that impossible XOR problem with no trouble at all.
And this wasn't just some clever little hack. This was a mathematical game changer. In 1989, a formal proof showed that an MLP with just one hidden layer is what's called a universal function approximator. So what on earth does that mean? It means that, in theory, a network like this can learn to model any smooth, continuous pattern as long as you give it enough neurons. It's basically a system that can learn, well, almost anything.
Section 4, How a Network Learns. So we've got this powerful structure, but the big question is still there. How does it know where to draw those lines, right? How does it actually learn from its own mistakes?
The answer is this really ingenious algorithm called backpropagation. It's basically a super clever system for learning from mistakes. So after the network makes a guess, it checks how wrong it was. Then it sends that error signal backwards through the entire network, and it tells each and every neuron how much it contributed to the screw-up.
And this creates a learning loop. It's a cycle. The network makes a guess. You measure the error. Then backpropagation nudges all the connections, the weights, just a tiny, tiny bit in the right direction. You repeat this process millions of times, and slowly but surely, the network gets better and better, minimizing its error with every single cycle.
Okay, Section 5, the Deep Learning Blueprint. Now this system is fantastic for clean data, but what about a messy, real-world problem, like an image? I mean, a single pixel doesn't really mean anything on its own. Before it can even think about drawing lines, the network first has to learn how to see. It needs to recognize meaningful features like edges and textures and shapes.
And that's the key difference between what we call shallow networks, the ones with just one hidden layer, and deep networks, which have a whole bunch of them. You see, a shallow network learns to partition data, but a deep network, it first learns to see the important features in that data, and then it learns to partition those features.
A really key architecture for this is the autoencoder. Imagine you feed it an image. The first part, the encoder, is forced to squeeze all that image data through a tiny, tiny bottleneck. To pull this off, it has to learn a super compressed summary of the image's most important features. Then, the second part, the decoder, tries to rebuild the original image using only that compressed summary. By getting good at this game, the encoder effectively learns to see the very essence of the data.
And this brings us to the blueprint for so many modern systems, like the deep belief network. It's a really powerful two-stage process. First, you have an encoding part that uses stacked layers to see and pull out the meaningful features from the raw, messy data. Then, it feeds that clean, useful summary into a partitioning part, which is just our good old MLP to do the final classification. So it learns to see, and then it learns to decide.
So there you have it. We've gone from a single neuron drawing one simple line all the way to a deep blueprint that can literally learn to see for itself. This whole journey, from simple lines to complex sight, that's the story of how AI grew up. It's the foundation for pretty much everything we see today, which really just leaves us with one big question. What are we going to teach these machines to recognize next?